Let's turn to the lecture note 3.23. And here we already explained the experimental result from Onuma and Okasawa in 1974 based on the concentration variation and the temperature distribution. Also, the fuel and the oxygen distribution for given kerosene spray flame compared with the propane diffusion flame. And based on the experimental comparisons, even for the next paper by Onuma groups in 1976 for NAX formation, and then they find out the spray combustion flame was found to be very similar to the turbulent gaseous diffusion flame in structures. And basically, we focus on the spray, the kerosene spray made by an airbrushed spray atomizer, which means the spray is under wear atomizing then, and also the kerosene has a lower boiling point. It is give us some understanding on this spray structure. Actually, they can be easily to be gasified to provide the fuel vapor to support the spray frame, and they do have similar structures compared with the turbulent gaseous diffusion frame. But for the next papers, the third paper for the Onuma's groups, they try to give a further understanding on using different kinds of liquid fuel. Now they try to use a heavy oil instead of the kerosene they used before. But for the utilization for heavy oil, because heavy oil has a high boiling point and it is not easier to atomize, then people always use some kinds of technology to the heating on the heavy oil. Therefore, in this experiment, they try to enhance the fuel velocity and atomize the velocity of fuel and atomizing air, and try to increase the viscosity of the heavy oil by heating it to 100 degrees Celsius at the nozzle inlet. Then this will help the atomization for using for the utilization of heavy oil. Now, and they try to compare the various species concentrations and also temperature concentration for both heavy oil and kerosene spray flame. Before they do the comparisons, and they try to figure out the differences between the droplet number density distribution for heavy oil spray and the kerosene spray. And this is the initial size distribution of the droplet for heavy oil spray and the kerosene spray in the experiment. And they find out the number of droplets more than 80 micron here is the 80 micron diameter is more numerous in the heavy oil spray, and the atomization of the heavy oil appears to be less good. Okay, which means that for the heavy oil spray, they do have a droplet size larger. They have a more number of for the larger droplets. Okay. And the droplet lifetime of the heavy oil spray is slightly longer than that of the kerosene spray. Yeah, this is reasonable to believe because the larger droplets heavy oil will have a longer lifetime for gasification. And this is the basic the basic differences between the kerosene oil spray and heavy oil spray. And then now they study the structures for the burning of the spray of a heavy oil spray and the kerosene sprays. And these figures, the left-hand side represent the various distributions on the flame axis for heavy oil flame, and the right figure represents that for the kerosene spray. Okay. When you compare these two figures, and then you definitely find out all the distribution are quite similar, right? Especially you can see the temperature distribution almost the same, and carbon dioxide, carbon monoxide, hydrogen, and also the velocity distribution indicated by the broken line. Okay, and there's the oxygen distribution, and they have a small differences, but actually they are quite similar for the overall distributions for species concentration, temperature, and also for velocity. And they look at the further to check the distributions along the radial along the radial directions, which means they take measurements for the cross sections at x equal to 10 centimeter, a little bit away from the exit plane of the injector, and they do the measurements and to see the symmetry distribution for species concentrations and the temperature and also the velocities, and then you find out they are quite similar for both cases. Okay, and they did some conclusion such that by comparing the frames of heavy oil and kerosene under the same conditions, it was found that the occurrence of droplets is about the same for both frames. This is very important conclusion from their experiments, and they say this may indicate that droplet behavior is not so different in these two frames. The frames nearly coincide with regard to the length and the width, and the major distribution of various quantities are similar for both frames. Definitely, this conclusion will give us the idea that how to use the gaseous diffusion frame to simulate possible location of the spray frames. But definitely, you understand this conclusion is based on their experimental arrangement. In the previous in the earliest two papers, actually they use an airbrushed atomizer to provide well atomized sprays, and they find out they have a similar frame structures for the spray and also for the gaseous propane. But for this paper, actually they try to make the heavy oil has a good atomizations. Then they heat it to the 100 degrees Celsius to reduce the viscosity, and you can find out the distribution for droplet size. Okay, actually, they almost have the same distribution, except the number of the droplets are more than 80 micron. They has a slight difference, but not too much, which means the droplet size distribution for kerosene oil, kerosene spray, and the heavy oil are quite the same. In this sense, they may have a very similar spray frame structure. Okay, up to here, actually, they give you a very clear understanding that in general, if you look at a spray with a good atomizations, that means that the droplet size distribution is relative move to the small droplet size, and they will have the largest larger spray angle, and with a good mixing with air. Then the all burning structure can be well described by using a gaseous diffusion frame. But basically, you need to understand the heat release coming from the gaseous fuel should be very similar to that from the liquid fuel. But for the next experiment, I will tell you they will show you some differences for the frame structure comparing the gaseous frame and the spray frame. And here, this work, this experimental work and simulations was reported by Kerr and Whitelaw in 1976. They consider the liquid kerosene spray, and they used the two different nozzles with diameter 0.25 millimeter as the frame one, and the other one is the 0.5 millimeter as the frame two. And for the frame one, they measure the droplet size distributions in the exit plane of the nozzle, they find out the saw mean diameter is around about 45 micron. The other one is about 100 micron, which means for the spray tool, the spray frame tool actually they represent they contains a larger droplet size distribution compared with the that for the spray frame one. And they use the same air pressures, 3.5 atmospheric pressure, but the cone angle are different. For the spray frame one has a smaller cone angle. This is basically influenced by the size of the nozzle diameter because the spray one has coming from a smaller size of the nozzle. And but for spray frame two, they have a wider cone angle. It's a 68-degree cone angle. Now they do the measurement and give us the overall flux structure plotted as the contours of the actual velocity and actual velocity fluctuation and also the temperature. Okay, you can see from this series experimental observation. Now we try to look at the differences between these two spray frames. Now you can see for the spray frame one, and you first look at the contour of the velocity and also contours of temperature. You can see there is the for the velocity. You can see initially the flow velocity inside of the spray frame. Actually, they will increase their velocities continuously to the downstream. And there is some kinds of boundary. The ISO velocity 9 show you there is the velocity decrease to the outer environment. And this can be compared with the temperature distribution in the contours of temperature. The isothermal 9 tell you there is the more dense region for the temperature variation. You can see there's a tell you this is similar to the they just give you the idea about the location of the spray frame you may have. You may think about the frame exists here, since at the frame location you will have a highest temperature and they have a larger temperature gradient to reduce the frame temperature to the surrounding temperature. Okay, and here you can identify the spray angle or spray frame may located at these positions, and these positions is very easier to look at. Is very to look at the diffusion frame is very closer to attach to the spray angle, and this spray angle it was already described as the 52 cone angle, and this steep temperature variations can be compared with the steep velocity variation, and to identify the location of your spray and the spray frame. Basically, for this experiment, the spray frame is very closer to the boundary of the spray. Okay, and you can see there is a larger fluctuation in the interior of spray because there is so many tiny droplets and they interact each other. Then they have a very large fluctuation. 50% is the maximum, but they reduce continuous to the downstream because the droplets gasified and become smaller or disappear. Then the velocity fluctuation will disappear. Okay. This is the first conditions flow structures for the spray frame one. And the contours for the isovelocity, isoturbulence, and isothermal show for the spray two in these three figures. And similarly, you can identify the spray frame is very close to the spray boundary, and this spray boundary show you this spray has a larger cone angle. Okay, and here you can see there is a larger velocity fluctuations in the interior of the spray for the spray two. As you remember, spray two has a larger injector size, indicating they have larger droplets you may have inside of the spray cone, and the interaction will become stronger, and the loss fluctuation will extend to the further downstream in compared with the spray one. Okay. And here is the tell you still they have the velocity distribution, and to show you a little bit coincide with the steep velocity variation coincide to the spread angle. Okay, and from those kinds of comparison, they find out the outline of the reaction zone. That means the frame zone, the spray frame, is indicated by the velocity and the temperature distributions, especially for the very steep variation on temperature distributions, and it roughly corresponding to the cone angle of the injector. Okay, and I think those kinds of experimental results give you some idea. Usually, the spray diffusion frame is very close to the boundary of the spray core. Okay, this is suggested from our previous discussions, because those diffusion frames are supported by the evaporate fuel vapor coming out from the cold core, and those fuel vapor coming out cannot because they mainly will depend on the diffusion, and they cannot extend too far. Therefore, your diffusion frame is very closer to the spray cone boundary. For the final experiment in the papers, actually they try to identify the differences between the structures for the spray frame and the gaseous frame, but they use the simulations to get some comparison. Here, let me describe a little bit about the mechanism for the simulations. They want to do the comparison between the experimental spray frames and the calculated gaseous frame. How to do the calculations? Actually, they try to develop their numerical schemes, and to compare with the existence experiment data. And those they use the similar initial conditions and the same available entropy. This is required for simulation, and they assume fast reaction and a crisp Gaussian probability distribution for scalar fluctuation. Also, they introduce the probability distribution for droplets. And here, before they go to the calculations, then I'm sorry, they did not consider the spread the spread calculation, because they just do the simulations on gaseous frame. They use the calculated gaseous frame to compare with the experimental spray frame. Okay, basically those kinds of scalar fluctuation is described by probability distribution, Gaussian distributions. Okay. And this mechanism, simulate mechanism, basically used to compare with experiment data based on hydrogen diffusion frame. Okay, this is the results, and the experiment data was taken from the Bigger and the Kent in 1972 for the hydrogen diffusion frame. And the first stage, they try to justify their the corrections on their simulation. And here you can see, based on their simulated mechanisms, the temperature, the simulate, the calculated temperature is shown by the line, by the curve, and the open circle point represent the experiment data, and then you can see the temperature distribution, and also the actual velocity along the central line of the jet are complete to coincide, which means that they justify their simulations on the hydrogen diffusion frame is where it can be well compared with the experiment data, especially on hydrogen diffusion frame. This is the first step to justify the ability for their calculations. Then they go to the next step. They use their simulate mechanism to have some simulation results to compare with the result from the frame 1 and the frame 2. Now, this is the first comparisons, and the solid the circle the curves represent the simulated results, and the open circle symbols and also the invert triangle symbols represent the experiment measurement, and especially for spray frame 1. Okay, and here typically you can see there is a good agreement between the similar result and also for the experiment result for the velocity for the actual velocity u. Okay, here this is the actual velocity. Oh, I need to see here. This is the distribution along the center line, for varying the actual positions. Okay, but the temperature they have underestimates, especially in the downstream region, and the highest temperatures occurs earlier for the gaseous frame compared with the spray frame. Okay, and the maximum temperature basically is smaller compared with the that for the spray frame 1, and furthermore, they bring the spray 1, spray 2 with the gaseous frame together and look at the, the the temperature distribution around the radial directions for a given actual positions. Okay, and the actual positions, the left hand side is in the upstream region, and the right hand side x over d equal to 7.15 represent the in the downstream regions, and you can find out the comparison between the calculated results, the gaseous phase for the gaseous phase indicated by the curve, and there is a two measurement from the spray 1. Spray 1 mainly is the black symbols, so solid circle symbol, and the open circle symbol represent the data from the spray frame 2. And you can see it has significant differences between these three sets of data. And in the in the upstream regions, the gaseous diffusion frame has the highest temperature distribution compared with the spray 1 and the spray 2. Spray 2 has the lower temperature distribution in the upstream, and when you go to the downstream side, you still can see the comparison, the significant differences between these three frames. Okay. And I tell you from the previous results, previous comparison, the first indication, the previous indication for this figure shown in page 3.30. They tell you the maximum center temperature of the gaseous simulation is less than that of the spray frame. Here, and you can see this is a maximum temperature occurs earlier for the gaseous frame, but spray frame has the higher maximum temperature and occurs in a further downstream. And this slightly give you the they will give you some suggestion. That means the for the spray frame 1, they have some droplets, and they will extend further to the downstream to reach the largest heat release in the downstream region to reach the maximum frame temperature, and this is basically influenced by the droplet appearance. And when you look at radial distribution for the temperatures, the radial profile of spray frame cannot be accurately simulated by corresponding gaseous frame. Okay, they have a big discrepancy occurs in the upstream region and also in the downstream regions. Then they give a general conclusion that the measurements do suggest a significant shortening of the frame length as the droplet size is decreased from SMD of 100 micron to 45 micron. This basically confirmed from the experimental observation. The frame length is shorter for the spray frame 1 compared with the spray frame 2. and the simulated gaseous flame is further shorter than the 15 micron spray flame. Actually, the gaseous diffusion flame had the shortest flame length. Okay, and those kinds of characters can be viewed from the temperature distribution. Okay, here, when you have maximum temperature occur here, then the temperature decrease. That means the flame become the burning will become weaker. Finally, they will disappear. That means that the end of the flame length. Okay. And then they give you the most important observation is that the representation of spray flame by calculation methods on the basis of gaseous flame must be extended to take account of droplet characteristics. Okay, here this is a very important conclusion to be considered, especially when you introducing spray with larger droplets larger droplets, then you need to think about the, the droplet lifetime for larger droplets. They will extend their, the appearance to the further downstream, and then they will give you the influence or extend the burning process to a longer distance. That means that you need to take account of droplet characteristics. By these two comparison, uh, one, one experimental result from the Onuma's series experiment, the other one from the Philo experiment, they tell you in some case, if you use the well atomizers, then you may try to use the gaseous diffusion flame to simulate the spray flame you may use in reality. But if you do have a atomizer provide larger droplets, then you need to consider the existence of the larger droplets because their lifetime is longer and they will extend the burning process to further downstream. You need to consider the droplet characteristics for those kinds of spray. Finally, I want to give you a conclusion, especially introduced by Shigeru and Lott in 1972. This is a very nice conclusion you should remember. And they try to use the velocity profile at a cross section for a given actual distance away from the injection port. And to let you know, the velocity profile distribution, the velocity distributions for different kinds of jets. And there is a full comparison. One is the so-called isothermal free jet. This is a cold jet, okay? And the second is an isothermal spray. This is a cold spray injecting out. And the third one is a spray with the combustion. That means that you have a spray flame with the spray core. And the finally is a gaseous diffusion flame. Purely is a gaseous fuel burning, and they try to bring these four jets together to investigate the velocity distribution for these four jets, and to let you have some comparison. But the main idea is they try is this. They try to introduce a so-called distribution function for the velocity profile and expressed by the exponential function here. The left-hand side represent the u represent the actual velocity, the average actual velocity, okay, capital U bar, and in the denominator represent the maximum actual velocity, and which occurs at the center point, center location at r equal to 0 along the center line. Okay, and there is the cosine. Cosine represents a non-dimensional radial distance, and this radial distance is non-dimensional by actual coordinates plus a. A is the effective origin of the jet. Usually, a jet has its own diameter, right? And they cannot be described just a simple point. And you need to extrapolate to get the single point locations. and those single point location were slightly lower than the exit plane of the injector by A, then you need to count A into your calculations. Then you will have a very good fitting for the distribution of velocity along the radial directions. Okay, and then the most important thing is there is the Ku. Ku represent the spread coefficient, velocity spread coefficient. If you have a large Ku, that means the velocity almost more concentrated in a small region. But you have a small Ku, that means the velocity distribution will spread to a larger area, larger regions. Okay, for example, you can see from the value here. For the isothermal free jets, here this is indicated by the diamond cycle. They have a smaller Ku, is around 92. But for the isothermal spray, where is isothermal spray? Isothermal spray actually is indicated by the square symbol. Okay, triangle symbol represent a spray with combustion. Both of them are very close together, equal, and the Ku is approximated by 130. 130 is small, is larger than 92. That means that the velocity distribution spread wider compared with the gaseous diffusion frame. And finally, I'm sorry. Gaseous diffusion Ku is equal to 360, but isothermal free jet has the smaller Ku, but has a larger, it's a wider spreading. Okay, this is the wider spreading for the isothermal free jet. The Ku is around 92, and the gaseous diffusion flame has the Ku equal to 360. Sorry, I make a mistake here. The gaseous diffusion flame diamond shaped curve has a larger Ku value. Okay. Now let us try to understand the differences between between these four jets. Okay. The first one, we try to consider the isothermal spray and also the isothermal free jet. Okay, the first two. Okay, here isothermal free jet Ku equal to 92. You can see this the line with the open circle. Okay, this is open circle, and the spray is around here. Actually, you can see the isothermal spray has a larger Ku compared with isothermal free jet, and it is 130 compared with 92. And the reason is the droplet of isothermal retain their momentum by larger period of time compared with the equivalent fluid particles of isothermal free jet. That means that, and the spreading, the exchange of momentum between the spray and the surrounding is less compared with the gaseous jet. Okay, since the droplet has the inertia and they will continuous forward actually to the downstreams. Okay, and the spreading to the radial direction is less compared with the gaseous cold jet. Okay. Consequently, the spread or the rate of decay of velocity is reduced by the presence of a droplet. Okay, and this is the first comparison compared with the isothermal free jet and isothermal spread, and those curves is confirmed by the experimental data. And for the isothermal spray, actually those data came from the Hastoni and Stockholm in 1971. Okay, this is the first comparison for the cold jet of gaseous and spray. Okay, the next one we try to do the comparison for the turbulent diffusion frame, and with non-burning. Okay, we look at the gaseous jet with and without burning. The gaseous jet, the cold jet, actually represented by isothermal free jet, right? With the larger, wider spreading. But for the gaseous diffusion flame, they were smaller the smallest spreading, it is definitely easier to see when you have a friend and you generate a friend, and the friend is always very close to the boundary of your jet, right? As we described for the jet diffusion frame. And this friend has a highest temperature, okay, at its locations, and these friends will have some thermal expansion to prevent the gaseous jet, the inner gaseous jet, to mix or to expand to the surroundings. Okay, which means that when you have a diffusion friend exists for the cold jet surrounds of the cold jet, then this high temperature boundary will push your cold gases and try to resist the expansion of your cold jet. Okay, then this is a comparison. That means that for the gaseous diffusion flame has the largest Ku equal to 360, and they cannot have widely spreading for a given actual positions. Finally, the comparison between the cold spray and the burning spray, here that means that we compare, there's two curves, one indicated by square circle, and the other square symbol, and the other one is a triangle symbol. Actually, they are almost the same, right? Which means the diffusion spray diffusion frame is almost attached to the boundary of the spray core. Okay, the value of Ku in the burning spray is closer to that of the isothermal spray. This indicates that in the region of the spray where Chiker and Loet's 1972 measurements, the effect of presence of droplets was dominant and more significant than the presence of flame. Okay, which means that when you still have a spray, those fuel vapor support by the droplets will become more important, since in the whole region of the spray core, they have a gasification from the beginning to the end. They continuously provide a fuel spray. Those fuel spray those fuel spray need to be supported by the droplet gasification, which means the supply of fuel vapor and also the diffusion of fuel vapor is limited by the gasification process of the droplet. Okay, and those fuel vapor cannot be strong enough to push your diffusion flame out of away from the spray core boundary. Then the diffusion flame the spray diffusion flame is always very closer to the spray to the spray core boundary, because they are waiting for enough supply of a fuel vapor coming out. Then they will maintain the spray flame burning. And I think these figures are very important to let you know the differences between the first one is the cold gaseous jet compared with the cold spray, and they also compare with the combustion spray and also the combustion of the gaseous diffusion flame. I hope these figures can keep you can bring these figures in your mind, and to remember how to justify the flame location compared with the location of your spray core, and also the jet boundary. Those kinds of conditions you need to have some understanding. Then you can use it to evaluate different kinds of jet configuration and also burning jet configuration. I think we close the discussions for the spray diffusion flame. Then we move a little bit to the so-called spray premise flame combustion. Actually, I will not spend too much time to describe it, because they will get more involved, because we need to introduce the asymptotic theory into this result. But I just tell you the possible structure you may have. Okay, the spray premise combustion can be is usually used for the liquid rocket engine, as I described earlier, because they use many injector for liquid fuel and liquid oxidizers, and they will provide easier mixing between the liquid fuel and the liquid oxidizer. gasified and mixed together. In application sense, they will have a good mixing for the liquid fuel and a liquid dropped, liquid oxidizers, and you will consider the burning structure may appear as a premix flame. Okay, and here they say the other application maybe you can look at the afterburner we described for the aircraft, right? The stabilization of spray on the flame holders. Okay, and those kinds of premix burning for the spray, they will give you the so-called the flame propagation. Then you need to go back to the premix flame features. You need to describe the so-called deflagration and also the detonation waves in these premix spray fields. Okay, and for the I just simply describe the possible burning structures you may experience, and those configuration proposed by Williams in earlier in 1985. Especially this is his book, and this is the classical book for us. It's a theory of combustion written by Williams. F.L. Williams is very famous and the top guy in combustion fear. Okay, now look at these structures. They try to give you the idea is this. We assume there is the fuel and oxygen, and maybe they have some products because the other region they will get involved with some products after the local combustions, and then they will bring from the left hand side to the right hand side. And simply say that if you consider oxygen is already oxidizer is already evaporates. Okay, and in this sense, you may have the fuel droplet with the fuel vapor occurs in the upstream region. Okay, there is the they show you the initial spray mixtures, and here after they travel a certain distance, a certain plate, because they will experience the flame, the chemical reaction, they release heat, and as you remember for premix flame, if you have a flame exist, then they will have a thermal diffusion to the upstream side. Those energy will give you the droplet, the fuel droplet, for example, here, they start because they absorb heat, right? They start to evaporate. Then they will go to the so-called purely vaporization region. In this region, because the temperature in the surrounding is high, but not high enough for ignition, then the droplets here, they just go through the gasification of vaporization process. Okay. Then after when they move closer to the back flame regions, since the temperature increase as we described, when you move to the upstream regions, the temperature reach to the ignition temperature. When you reach to ignition temperature, then certain droplets will be ignited as a single droplet burning. Then you can see here they for these regions, actually, they get involved with the bulk homogeneous combustion. The bulk homogeneous combustion actually refer to the premix burning because in the upstream side, you already have some fuel vapor coming out. Those fuel vapor will premix with oxygen in the upstream zone. Then they will have a so-called premix feature, premix structures in these flow regions. Then the temperature is high enough, then the bulk premix flame is ignited. Then this belongs to the so-called homogeneous combustion. Homogeneous, as I mentioned, homogeneous means in that flow field, you just have a single phase. In this sense, in this region, actually, they represent the gaseous burning, okay, homogeneous burning. But in this region, you still have a certain amount of fuel droplets. And those fuel droplets, when they move into this region, they will reach the temperature near the your droplet reach the ignition temperature. Then single droplet burning will occur. Okay. Now, when you have a bulk homogeneous combustion get involved with many tiny droplet burning, then you will have a so-called the heterogeneous combustion. Heterogeneous combustion means in the combustion field, you have a two-phase. One is the gaseous phase combustion. The other one is a droplet burning. This is get involved with a liquid droplet and need to go through the gasification and burning. But anywhere there is a liquid phase get involved, then we call this a so-called heterogeneous combustion. Usually, you may consider a homogeneous combustion means that in this control volume, all the chemical reaction occur in gas phase without any solid phase or liquid phase get involved in this region. But in the case of the spray, usually you will have a droplet burning or droplet gasification or droplet evaporation in the control volume. Then we will look at this combustion mechanism as a heterogeneous. Okay, and those heterogeneous combustion, the area for the heterogeneous combustion maybe extend longer in the downstream side, which means the gaseous fuel complete burn out at the boundary, downstream boundary of the homogeneous combustion. And finally, you may have a droplet has a larger droplet size, and they will have a longer lifetime. They will extend further to burn in the downstream. Okay, and simply say that you can experience that by two ways. One way, the part of the gasified fuel vapor will move from the upstream to the downstream, and at the certain locations, they will have a back premise flame burning belong to the gaseous combustions. And the other part you may think about there is some droplets with larger size. Initially, they're coming from the upstream side with larger size, and they start to evaporate as the temperature high enough. Then the droplet will release some fuel vapor continuously, but the droplet size still bigger when they attach when they go to the back flame, back gaseous combustion. Since back gaseous combustion has a very high temperature, then droplet will be ignited. In this region, you still have enough oxygen. Definitely, you need to assume the oxygen concentration is large enough from the upstream to the downstream site. Then droplet will be ignited, burn as the diffusion flame, spray diffusion flame, and a continuous move to the downstream side. If oxygen is still left, then you can finish the droplet combustion in the downstreams. Okay, at the end of the combustion process, you may just have oxygen left and products left. Depends on the equilibrium ratio you may have from the beginning. Okay, then you can figure out that the condition for the burning with the gaseous combustion and the droplet burning will depend on many parameters from the upstream side. For example, if you think about, yeah, this is a very good thinking, is if you have a rich condition means oxygen may not be enough to completely consume with the fuel. Even they will get involved with liquid drop, right? Then that means the oxygen may not be enough to burn out, to burn with the fuel vapor coming out. Then finally, maybe you guys think about after the homogeneous combustion, you will have a few vapor left and also droplets, right? Because we do not have enough oxygen to complete burning. Now, in the downstream side, you still have a droplet evaporation. But for the lean case, oxygen is good, is large enough. In this case, you may have a droplet burning in the downstream side. Then you will find out when you try to figure out the whole combustion catalyst for the spray premix combustions, and you need to adjust the initial condition. Then they will give you the different combustion mechanisms. And I will try to give you some understanding because they will get involved with the very complex calculation for this model. Okay, but anyway, we will describe it for the next part.